Happy Earth Day, everyone, and welcome to the final installment of our Accelerating Toward P2 webinar series. Today's session, titled Compressed Air and Energy Efficiency Programs, will highlight the Alabama Industrial Assessment Center and provide some helpful best practices for compressed air systems and other energy efficiency opportunities. My name is Michael Raspberry, and I am the Associate Director of UA SafeState. So a little bit about UA SafeState, for those of you who don't know us, we are a program that consists of an occupational safety and health consultation program. They are the state OSHA consultation program who are able to assist small businesses with safety and health consultations. So you can just sign up on their list, and they'll come out free of charge for small businesses. And they'll do a full assessment of your safety and health program. We also have a training and conferences group that offers safety and health and environmental training. We also are host of the Alabama Governor's Safety and Health Conference, which will be held again this fall at the Perdido Beach Resort. We also have an OTI, or an OSHA Training Institute, where we can train the trainer for facilities and help your trainers teach safety and health practices to their staff. And then our environmental program. So we in the environmental program work with companies across the state and beyond on environmental compliance issues. We can come in and do full environmental management system reviews, including ISO 14001. We also offer a number of environmental training opportunities for you to take advantage of. One of our programs is the Pollution Prevention, or P2 program, and this is partially funded by a grant from the U.S. Environmental Protection Agency. And through this program, it allows us to provide businesses with technical assistance and training to find ways to reduce waste and save money. And so an example of the type training that we're able to provide under this program is like the webinar that you're attending right now. These assessments examine energy efficiency, water conservation, chemical use, and waste reduction opportunities. The best thing about them is there's no cost, no obligation, they're confidential, and you'll get a full report of all the recommendations that we make when we visit your facility. And so we will provide some contact information later on how you can contact us and have us come in and evaluate your plant site. So here are a couple housekeeping tips. Everybody has been set to mute to eliminate background noise. We are recording this webinar right now, and it will be available on our website. If you have questions, just feel free to click on the chat feature and enter in your question there, and we'll make sure that all questions get answered. And then there will be a post-webinar survey. And without further ado, I am pleased to introduce today's speaker, Dr. David MacPhee. Dr. MacPhee is Assistant Professor in the Department of Mechanical Engineering at the University of Alabama. David also serves as Assistant Director of the Alabama Industrial Assessment Center, and he is going to share more about that with you right now. So David, if you would share your screen, and feel free to share your camera, and I'll turn it over to you.
Thanks, Michael. Yeah, hold on. I'm about to share my screen. Let me see. How am I going to do this? You think I would have done this beforehand? No, I'm almost there. Here we go. Let's share my PowerPoint presentation. Can you see that?
Yes, it's not in.
Okay, so let's do presentation mode from beginning. Usually good practice to start from the beginning. While we do that, I'm going to put my video on. I don't know why, but I tend to talk with my hands a lot, and so I'm going to put my video on if that doesn't scare anybody. So you can see me here. I didn't wear a colored shirt. I'm sorry, but there's some boxes in the background. Hopefully that doesn't mess you up too much. Hi, I'm David, and I'll be talking to you about compressed air for the next, I don't know, hopefully not more than 35 minutes, but we'll see. I get rambling sometimes when I get excited about stuff like compressed air. Okay, so as I said, I will start the slideshow from the beginning. Are we all good?
It's not, yep, we're good.
Okay. Well, Michael, thank you. UA SafeState, I want to say thank you for putting this series of webinars together and for having me out. Not physically, I guess, virtually. This first slide is really busy, but I have to give a shout out to all the organizations that make my job possible. Along the bottom here, hopefully you can see my cursor, but we've got USDA. I actually do some projects with Department of Agriculture to do energy audits and renewable energy assistance. We'll talk about that in a second. This big picture up here is the Industrial Assessment Center. As Michael was alluding to, I'm the assistant director of this center and do a lot of work for industry in terms of energy audits and energy usage. And over here we have what I found to be the best picture of how a regular, a typical air compressor works, or what it looks like on the inside. We'll get back into that in a little bit, and that kind of stuff is really interesting to me. So anyway, yeah, so that's all about me. We're going to talk about compressed air, and so let me go forward. Today we'll talk about, I'm sorry, before we get to technical things, I'm going to talk about our Industrial Assessment Center, that's IAC program, my Department of Agriculture program, which is the Alabama Rural Energy Program. So that'll be 5 minutes, but I got to have my due diligence there to promote our program, because we do give pretty decent free services to offer energy advice to manufacturers and farmers, actually. So anyway, we'll get over that. Types of air compressors, compressed air in general, performance, and I think the most important thing is how do you save energy and associated costs in compressed air systems. And then we'll have time for question and answer period. I'm also available by email if you are viewing this not at 11 a.m. on April 22nd. Anyway, so before we get started, I said I would talk about the IAC program, the Industrial Assessment Centers. This is a collection of 28 centers across this great nation, which are centered at academic institutions, and there are two main goals for these centers. One is to educate the engineers of tomorrow in energy savvy practices, and gives them a really good opportunity to get some hands-on real world experience before they go out in the workforce. And they do that by working in this center. So we employ, I think like 10 or 12 undergrads at the time being in our center, and about 3 or 4 grad students. So Department of Energy funds this whole thing, as you can see on the bottom here, specifically the Advanced Manufacturing Office, the AMO. They fund this whole thing with 2 goals in mind. One, students, they invest in the future of this country in terms of engineers, energy savvy practices, and 2, they actually want to help the manufacturers out. And so there's a certain range you have to fit in, but they're trying to make manufacturing to be more cost competitive. So let me go back here for a second. So this is, a red circle around the elephant in the middle. That's where University of Alabama is. The nearest centers to us are Georgia Tech over in the east. We've got LSU, Tennessee Tech. I've worked in the Alabama Industrial Assessment Center for 6 years now. Before that, I was a member of the San Diego State University one since 2009. So I've been doing this for going on 12 years now. And so this is the Alabama Industrial Assessment Center, which has been around 15 years in service. We've done 268 energy assessments, and these are pretty comprehensive energy assessments. And all this other stats you can take in at your leisure, but a lot of recommendations. Recommend a lot of Tera BTUs and energy savings, and I think most impressively, we've trained 122 students. And all those students are going to get real world knowledge of how manufacturing is done before they leave. Anyway, so that's my my shtick or my spiel for the Industrial Assessment Center. thing. I don't know if I mentioned this, but it's completely free, sponsored by Department of Energy. And you know what? If you are if you work for a manufacturing entity in Alabama, I might tell you, hey, if it's something you're interested in, you do have to fit into these requirements. You got to make something, so it turns into it's a value-added process. You got to be in manufacturing. You know, if you are, your energy bills must be between 100,000 and 2.5 million a year. That's kind of the sweet range for Department of Energy, so that you probably can't afford your own full-time energy engineer, and you're big enough to worry about in terms of what Department of Energy wants. This number 3 here, you got to be within 150 miles from IAC. Yeah, that is, we don't want to drive 6 hours to come to your plant for a one-day assessment. Anyway, so we've been doing this for a long time. We're very good at it. If you're interested, I'll give you some contacts at the end of this presentation. We're very good at assessing, as you might guess, compressed air energy usage, but we also do a lot of other things related to natural gas, boilers, ovens, related to electricity. We're very good with pumps, water chillers, cooling tower. I mean, all the things that use energy in a facility. We can help you identify areas to save costs and save energy and associated costs pretty well. Okay, so I think I've talked a little too much about that already. I'm long-winded on this stuff because I feel pretty passionate about it. Another smaller program that I run here is the Alabama Rural Energy Program. Another free program to you, but you have to be a rural small business or an agricultural producer. So if you're outside of a city, you could be a manufacturer and you might actually qualify for assistance under renewable energy assistance under this contract. And by renewable, I mean, hey, if you think that solar power or wind power or bioenergy might be something that you might could get into your energy portfolio, so to speak, or if you think that could help you out in any way, we can help you free of charge figure out whether that's something that you want to undertake. And so, yeah, again, if this is something that interests you and you qualify being a farmer or in a rural area, contact me after this. Okay, so now I'm done, I promise. And we're going to talk about air compressors, okay? So, bit of a conversation shift. Okay, so compressed air. Compressed air is used in a lot of ways. Okay, so I'm not going to go over every way that you can use compressed air in a facility or in your garage or whatever, but this is the general outline of how a compressed air system might be laid out for a larger entity, for a larger system. So over here you got, it looks like 2 air compressors. A lot of times you see these boxes here. The air compressors they're in these boxes, so you don't have to look at the inner workings. And I'll show you what that looks like in a minute. But you got compressors, they're making air. That air, turns out air has water in it. Who knew, right? And so when you compress air, the water, you need to get that water out of it because it's going to condense out and ruin things. So it goes through a dryer, and there's a pressure drop associated with going through. And there's many different kinds of dryers. We're not here to talk about dryers. It goes through an air filter, and then it goes into an air receiver, a giant tank that ends up being, a capacitance. It just ends up supplying the system with air. You need storage to deal with demand and intermittent demand of the system. And then the compressed air comes out of this air receiver and it goes all over the plant. People are using it to, these shadows here are using it to, I don't know, they've got air tools, pneumatic driven air tools. These are little filter regulator lubricators. It's for air tools. There could be storage at the other end of the plant. This is an example of best practices for compressed air, having a loop system all the way around and not just one pipe going all the way down. Really helps out with keeping pressure constant and in the system, and having storage at both ends of the facility. Also good. We'll get back into that again later. This is an example of a compressed air system. You might be using this for air tools. You might be using this for maybe you have a stamping process and you have these big, I don't know, you use compressed air for a lot of things. And we're going to talk today not about so much about the demand side of compressed air. I'm going to talk mostly about the supply side compressed air, because that is where I think the low-hanging fruit can be best tackled. Actually, I'll be talking kind of on both sides. So let's get back to energy usage for compressed air. So based on the Department of Energy's guidelines, compressed air can account for, they say, around 10%, but in our Alabama Industrial Assessment Center's statistics are a bit higher than that, sometimes up to 20% of total electricity usage, which is a pretty large amount. So it's not a nothing. It's almost always between 10 and 20% of your total electrical usage to make air. And so there are two main types or families of air compressors that do this. And so those of you who are, have a garage, that's one type. It's called a reciprocating type. And so let me just get a little picture here. You might have one of these in your garage, okay? And that's the reciprocating. There are pistons in this thing. And that's a type of air compressor. In fact, a lot of the older facilities had giant reciprocating compressors. If you're lucky enough to walk into an older manufacturing facility, some of these compressors could take up the space of an entire room. They're super loud, super noisy, but they really end up being very efficient for reasons I'll explain later. But this is an air compressor as far as most of us see it, okay? There's a tank in the bottom. That is your receiver. There's this motor here. Hopefully you can see my cursor, but there's a motor here. It's driving a belt that's driving a crankshaft that has these two compressors going up, or these two pistons going up and down, and it's compressing air. So that is a type of air compressor. If you want to look at the intrinsics of what's going on here, it's kind of neat. I mean, usually there's a lot of the smaller ones are two-stage air compressors. So they got a big piston here for the first stage, and you'll notice a small pipe with some rings around it. It's a heat exchanger actually to cool it off. So there's an intercooler between the two stages, and it gets compressed to high pressure in the second stage, and then it gets put back in your receiver. This is a cut through of the pulley that the crank that's driving the crankshaft, that's being driven by a belt, that's being driven by the motor. I'm talking fast, but because I've got a lot of coffee into my system right now. So that's a reciprocating compressor, and again, they're very common. However, they're really expensive to make in high air volume settings. You don't really want to. You don't want to buy a new compressor because it's more expensive to make if they get a lot bigger. You don't want to buy a giant 300 horsepower reciprocating air compressor. You want to buy what is this should be red on rotary screw, but this is a rotary screw compressor. And so almost every manufacturer you're going to see is going to have or every compressor that's between 25-ish, probably 30 or 40-ish horsepower, up to about 250 to 300 horsepower. That's the range that almost every facility we've been in Alabama and in California, they're going to use rotary screw compressors. And we're going to talk more about those because I think it's important for us to know how air is compressed to really understand how to tackle getting more out of your kilowatt hour of electricity. So this isn't what, I mean, the box that you buy an air compressor in looks kind of like what you see here. Some of it's a little translucent just to give you an idea of what's going on in the inside, but really you go up to an air compressor in a facility, you just see this Ingersoll Rand, and it's going to be, in this company, it'll be beige. You'll be locked away from all the neat stuff on the inside of this. I did talk about there being two types of compressors, right? So reciprocating rotary screw are both positive displacement compressors, meaning that they squish air into a receiver. There are other types. They're called dynamic compressors. One is a centrifugal compressor. We do see those sometimes. They are fundamentally a lot more complicated to deal with. But if you have questions about how to deal with those, it would take a little bit more time than what we have today, but suffice to say that centrifugal compressors, if you can use the air that they're making, are much more efficient than rotary screw. And Axial flow compressors are, I don't know, I use them for jet engines is one example, but I've never seen them in a industrial sense. Maybe for power production, I don't know. So suffice to say, don't worry about dynamic compressors for today. 99% of the people out there are going to either have this type of compressor, which is a reciprocating piston compressor. And if that's the case, don't worry about how you're operating it. Worry about leaks and pressure. We'll get to that in a minute. If you have a compressor that is a rotary screw compressor, well, strap yourselves in. We're going to go and talk about rotary screw compressors in a lot more detail. This image was not so fuzzy when I put it in this morning. I'm sorry about that, but this is what happens when you open up an air compressor cabinet. Okay, if you were to strip away the beige doors on this is what it would look like. Okay, I think this is an Ingersoll Rand compressor. So how do they work? Okay, so in the beginning of this presentation, I showed you an image of two screws that were kind of intertwined. Okay, and if you can go back and look at that if you want, I'm not going to scroll all the way back right now, but that's these screws right here. So essentially what those screws do when they rotate, they literally take air and they squish it up against the outsides of the casing, and they literally just by the way they rotate, they squish air from one end to the other. That's the best I can example. That's the easiest it can be explained, and it's not much more complicated than that. So that's these screws here. So air from the room goes into this filter here, where obviously you would want to filter out dust and whatever from this air. Then it goes into this one end of the screw, and it gets squished to the other end of the screw, and then it goes into this weird air oil separator. Now this is where I believe it doesn't have a lot to do with energy efficiency. Well, it can, but I believe it's important for us to understand how these screw compressors work. They're all, for the most part, something we call oil injected. So when you compress air, it gets hot just by physics. I mean, the ideal gas law. Okay, if you go back to high school physics, it gets hot. Furthermore, there's these screws that are rotating against each other in that assembly there, and they're also sliding up against the casing. Okay, so there's just an incredible amount of heat. You'd be amazed at the amount of heat generated because it's actually about 70 to 80% of all the electricity that goes into here ends up being converted to waste heat and not pressure energy. So that's something that's unfortunate. We'll get back to that in a minute. So this stuff gets really hot. So what do they do? They spray oil. There's literally oil that gets sprayed into these casings here, and it cools everything down. It lubricates and it cools. And so at the end of these screws, you get super compressed air, but it's also got a whole bunch of oil in it. And so it goes in this air oil separator. Oil goes to the bottom, compressed air goes to the top. The compressed air is filtered in here somewhere. And both the air and the oil, which are both really hot, go through an aftercooler. And that is what this whole thing is here. So if you go up to an air compressor in a manufacturing facility, and you'll notice it's loud, because these big motors are these driving these screws, but also there's a really big fan in here that is cooling the air and the oil through a big heat exchanger. And so if you put your hand above it, it'll be 130, 140 degrees Fahrenheit. And it's at a pretty high flow rate. So this is just an overview of how compressed air works. So at the end of this, you have pretty hot air. It's not so terribly hot. And sorry, my phone just rang. It's pretty hot air, and it goes out to the receiver. Well, it goes to a dryer first, then a receiver and whatnot. Okay, okay, so this is how 90%, I'll say, of your compressors work. And the next thing I want to talk about is, well, now that you know how compressors work, and let's just say you're interested in reducing energy usage, how do we even get a handle on this? My advice to you first is to find out how much energy it's using. And I'm pretty sure that you don't have a meter, an electricity meter devoted entirely to this compressor. So you're going to have to find some sort of baseline. And this is a very loaded screen here. And I'm glad this is being recorded because you might want to have to go back to this screen later to figure out what I'm talking about, because I'm going to go over a lot of things fairly quickly. You can figure out how much energy your compressor is using a number of ways, as you might imagine. The way that I do it is I physically go to the plant and I get a plant, someone who's working in the plant to open up that cabinet. And by the way, just a warning, don't do this unless, it's just a warning. You could get electrocuted if you're not comfortable inside cabinets. And what you should do is get the facility to open up the cabinet for you and do this for you. But what we do is we put a current transducer, it's a little clip, onto one of the three-phase leads going into this compressor. And that's called data logging of current. So this is what we do with every facility we go to. I've got a little picture here of this HoboWare data logger. It's a type of data logger you can use. We use a slightly different one, but this one served the purposes of this presentation. So you go to these compressors, you put a little data logger on one of the three leads, and that's the current. And you can get a surrogate for power draw by doing this equation. Might want to write this down if you're interested in doing this for yourself, but you have to have the voltage, that's V, times the amperage, which is A, times the square root of this Greek letter, I think it's phi. And that's the square root of the number of phases of power that you have. That's going to be 3 for almost everybody out there who has a facility that uses 480 volt three-phase power. If you have, 120 volt, then this is just square root of 1, because that's we have single phase power in our homes. Okay. So if you want to know the power being drawn by the compressor, once again, voltage, which is a lot of times 480, times the amperage, which is what you're measuring, times the square root of the phase, which is 3, times some sort of power factor, PF. This is where I'm not going to draw you into the weeds. I'll try not to, but the power factor is the ratio of real to apparent power. And if you don't know what I just said, let power factor be 0.8. And if you do know what I just said, you might want to check into your motor specifics to find out what power factor should be. It'll be around 0.8. Just leave it at 0.8 and let's continue. So you can get the power drawn by this compressor. What you want to do is you want to figure out, hey, best case scenario, you log the power for an entire year and find out how much power this is drawing. You can do that again with the current transducer we have. You can actually log power, but you need a power quality meter, which are expensive, and we don't do that because it's just too complicated. So I would say, unless you're really into logging of the power, don't bother with that. You can also use one of these little handheld things. Okay, this is actually super easy. This is a Fluke Bluetooth, so it hooks up to my phone, and sometimes it's really neat to go up to an air compressor and loop this thing around one of the 3 leads and sit there and record on your phone a CSV file of amperage for a couple minutes. And sometimes you can get a good idea of how an air compressor is being used by just monitoring it for a few minutes. If the people in the plant say, if the plant personnel say this is kind of how a normal hour of operation. So you can do all those things. Let's just say you don't have any equipment whatsoever. You still can go to the control panel by fiddling around with the numbers on there. Don't stop it or anything like that, or change the pressure settings or anything like that. But you can go through the information in the control panel and figure out how often, if it's in a load-unload configuration, and we'll talk about that in a minute, but you can figure out how heavy it's being loaded by looking at how many hours it's loaded and how many hours it's unloaded. You can also look at how it's loaded by looking at the modulation of the valve, the position of the modulating valve. And again, these 2 bullet points here are some things that I haven't talked about yet, so you don't know anything about load, unload, or modulation control strategies. So don't worry, it's coming. So get excited. Anyway, so let's just say you can find out the power power that's being drawn by this equation here. This ends up being power drawn in watts. So if you want to figure out how many kilowatt hours your compressor is using, you divide that by 1,000. That's what this 1,000 is down here to get to kilowatts, and then multiply that by number of operating hours. That's what OH is. And that way you get kilowatt hours per year. And I think in an afternoon, if you really, observed, or you had one of these uh, amp transducers, even the handheld ones, you can get a pretty good idea of how much electricity your compressor is using every year, and even more importantly, how heavily it's loaded. And we'll talk about that in just a minute. This is where things get exciting, and we'll talk about control strategies right now. So there's basically 4 general control strategies. Now we're talking about rotary screw compressors. That's how the majority of almost every compressor if you're concerned about your compressor, it's going to be a rotary screw compressor. And there's 4 general ways to control this. Okay. And this is kind of in order of, I think, the most prevalent or most common to the least common. Okay. So first of all, okay, I'm going to explain what this graph means in just a second. So let's just say you are monitoring the current going into this compressor, and you've exported that to an Excel spreadsheet, and you figured out the power in watts or kilowatts over the time. And so this is kind of what it would look like if you were in a load unload control strategy. So when you buy a compressor, it comes with 1 or 2 control strategies that you can switch between. Usually it's just one control strategy. And this is what it does to keep pressure in your system so you can use compressed air in your facility. Okay, load and load. So what happens is it's a lot like a thermostat for an HVAC system. Okay, what you do is you set a pressure band. You say, okay, we want this to be between 105 and 115 psi. When the pressure in the system drops down below 105, it kicks on, and it'll kick on until it goes and hits 115, and then it'll unload. Okay. So that's exactly what this is doing. So we have load, and I drew this using Microsoft Paint. So I apologize if it looks horrible, but I don't know. I think it was better than me drawing with my hands. So you have a load fraction and an unload fraction. Why don't they shut it off? You might be asking. Well, that's number 4 down here, on off. That's kind of really bad for motors. If you know something about motors, you'll know that you're not really supposed to turn them on and off a lot, because what happens is that it heats up the windings. The motors are driven by copper wires, and so it heats those copper wires up to the point where if you turn a motor on and off a bunch of times, it's just going to blow up and overheat, and things will melt, and you'll be looking for a new compressor. So what they do is, instead of turning off, they just unload. And so what they'll do is, instead of the screws driving air to the air compressor, the compressed air region, the screws will just be driving air to nowhere. So it'll just be like, they're just moving. The screws are moving and not really doing anything. And that's the best way to, that's one of the best control strategies, the most common control strategies. So you load, you hit your pressure, you unload until you hit the low pressure, and you keep going. The great thing about this is it's super common, super easy. A lot of older compressors do this. The unfortunate thing is that the compressor still uses energy when it's unloaded. I may have overestimated here, but 30, sometimes 40% of the full load power is being used even when the compressor is not making air, which makes it kind of inefficient. It's still more efficient than inlet modulation, which we'll talk about in a second, but it's not the best thing in the world. I also have another thing here. Watch out for short cycling. So again, another tidbit, and this will be maybe discussed later in the presentation, but if you do monitor power and you see that this here, okay, is not getting down to a flat portion down here, you want this unload portion to get flat at some point in time. And if it's not, it's called short cycling. And that means you're not fully unloaded. And it means you don't have enough storage in your system. And if you don't have, you need enough storage for your system, especially if there's high demand intermittent air being required. So just watch out for short cycling. It's actually bad for the compressor, and it wastes energy. So that's one way to know you don't have enough storage in your system. Okay, so that was load unload. Okay, so now we're going to talk about inlet modulation, which is also very common. Inlet modulation is essentially like a valve. Okay, so if you've got well, I guess I can there's no really way to explain it other than there's a butterfly valve, and it controls the amount of air that's being allowed into the screws. Okay, and so it tapers off if you're not using as much air, and it'll open up if you're using more air. So it's basically just a modulating valve that does this. Why would you do this? Well, you can actually maintain a consistent pressure very easily, and your ability to respond to the dynamics of the system is actually way better because you can just very easily just rotate this little valve in order to maintain the pressure in your system. And so I've drawn another Microsoft Paint image here of the compressed air power over time, and it's trying to keep pressure in the system, and that's kind of what I've drawn here. It also apparently is very similar to what you would experience with a variable frequency drive. A variable frequency drive does something different. Okay, these are like the top of the line in double screw compressors, and the way that they do this is they actually modulate the frequency of electricity to the compressor. And so your frequency is going to be about 50 hertz here. And that causes motors to run at some multiple of 50 hertz. And so what you can actually do, it's a really neat thing that I don't really understand because I'm not an electrical engineer, but the frequency can be modulated, or the frequency can be changed to change the speed of the motor. And so it's actually a more efficient way to respond to system dynamics. It's way better than all the other things, VFD. So if you ever see a motor controlled by a variable frequency drive, that's a great thing. So I've got some more notes down here. As I said, modulating is great for maintaining constant pressure. One thing I didn't mention is that it's very inefficient if the air demand is low. Okay, so you can imagine if the air demand is very low, you still have this motor running as loaded as it can, but you're closing the valve. And so the motor is really, and the screws are really just fighting against that valve and the inlet valve, and it not really fighting against system pressure. So it ends up being incredibly good for maintaining constant system pressures, and it was very, very, very popular up until variable frequency drives became a little cheaper. But inlet modulation is good, but it's also incredibly inefficient, and we'll get into that in a minute. Actually, right now. So these are rotary screw characteristics. This might be the most heavy figure in this whole presentation. And I realize I'm going slower than I should, but anyway. So let's pretend you have, okay, so on the vertical you have power, 0 to 100%. On the horizontal you have capacity. That's in your cubic feet per minute of air you're delivering to your plant, 0 to 100%. No matter what you do, you're going to have, no matter what control strategy you have, if you are delivering the max amount of air that the compressor can handle, it doesn't matter what you're doing. The motor is just going to be running full out the whole time, and your control strategy doesn't matter. But if you get down to areas where you're not delivering a lot, you'll notice that start-stop, we haven't talked very much about that, but that's like a reciprocating compressor. Reciprocating compressor is basically as efficient as you can get. Not listed here as variable frequency drive, which is the exact same curve as the start-stop. So let's just say you're at 50% capacity. Let's just say you got an air compressor that delivers 500 cubic feet per minute at 100 psi, but you're only using 250 cubic feet per minute. You're using the least amount of power for your start-stop, your variable frequency drive. Then next up, the next best choice is a load-unload configuration. And you go way up here to modulation. As I said, modulating is very good for maintaining system pressure, but you are wasting a lot of energy using modulation controls if you have a low air demand in your system, unfortunately. There's no way to know that unless you actually look at the power drawn from your system and compare that to the maximum power drawn in your system. So I think I've gone into the weeds a few ways, and I'm sorry, but I teach an entire class on industrial energy usage, and the compressed air section is like it's like 6 or 7 lectures, like 2 or 3 weeks. So I'm trying to condense this all. I'm sorry if I'm losing any of you on the way, but I'm just going to tell you the 3 ways that I would recommend you to save energy. The easiest way is to reduce pressure. More advanced is reduce leaks, then modify your control strategy. Okay, so reducing pressure is something that might be a no-brainer for everybody. But I'll tell you something right now. When you reduce the discharge pressure on your compressed air system, you save energy in 2 ways. One, you don't have to compress the air to as high of a pressure. That might seem really simple and straightforward to you. But 2, you're actually having to intake less air as a result of this. So you have to use less air as well. And so there's like a double twin win sort of thing when you reduce air pressure. A rule of thumb that we've verified many times using more sophisticated means is that if you can reduce 2 psi in around the 100 psi range, you're going to realize a 1.6 reduction in energy usage. So we recommend every plant that we go to, unless they have a process that requires a certain compressed air pressure, we recommend they just say, hey, you know, let's do a 10 psi drop. Then you get an 8% compressor energy savings. That ends up adding up quite a lot, and it's very easy to do. What I usually recommend is that the plant manager maybe goes up to the air compressor and maybe goes down by 1 psi and waits for a week. And if no one notices anything, then why not do another psi? And then just keep doing that until someone at the back of the plant who's using the grinding wheel says, hey, this isn't working. Then you bump it up a couple of psi, and that's, I think, the best you can do at that point in terms of something that's very easy to accomplish. And we'll get into some actual numbers later, but I mean, reducing pressure is pretty easy. Reducing leaks is incredibly important, but it's difficult to figure out the leaks in your system. I will say now that leaks can account for 40% of the total compressed air usage in a plant. I've seen it way higher than that. I've seen incredibly inefficient uses of air. I've seen 1-inch hoses just venting air for no reason other than to, you know, cool someone off. Okay. As I said before, 80%-ish of the energy that goes into an air compressor goes away to waste heat. So if you're using compressed air to cool you off, that's 5 times more energy than you should be using a fan. Okay. So just keep that in mind. But we have seen leaks be incredibly prevalent in some systems. If you want to diagnose leaks, you fix fittings, seals, all that stuff. You can do that with an ultrasonic leak detector or a specialist to analyze. And that's where I'm going to talk about myself a little bit and the Industrial Assessment Center. We can come in there, and by putting data loggers on your compressors and knowledge of a time when the plant is perhaps out to lunch, or you know, an hour before operations start, we can figure out, based on what your compressors are drawing and their characteristic curves, we can figure out the amount of air that they are making just to feed leaks. And so that's incredibly effective. And leaks are a huge thing. And so you got to get your handles on leaks. So that's something you have to do every couple of months, every 6 months, because those fittings, they I mean, you can never stop leaks. You can only slow them down, right? And so reduce pressure, reduce leaks. Those are things that you could probably do right now without really any specialist. But if you want to modify operations, that's I would call expert level. Not really expert level, but hopefully you'll have an idea about it now. But you can change the control strategy sometimes by going to your compressor. There may be a way for you to seriously change it from load unload to modulating with unloading, or vice versa. And so I've seen this many times. Or you can actually switch out a compressor for one with a VFD, or you can call some vendors and see if you can install a VFD on your air compressor if they're load unload. So here's an example. Okay, so I went through all this, and we learned a lot about compressed air. Hopefully you learned something about compressed air and air compressors, but here's an example Typically, for every 100 horsepower of rotary screw oil injected air compressor, you're going to get about 450 actual cubic feet per minute of compressed air into your system at about 110-ish psi. Okay, so let's just say you go in your plant and you have a 100 horsepower compressor, and this is probably pretty close to what it's going to be delivering, and your outlet pressure is 110 psi, and your plant operates 5 days a week, 12 hours a day, 52 weeks per year, gives you this many hours per year. This is actually kind of a low operational hours per year for a compressor. I've seen them very close to 8760, which is the maximum amount, especially for those manufacturing facilities that are operating, I don't know, 18 hours a day, 6-7 days a week. Some of them are 24/7. So anyway, you've got this compressor. You go out, you measure the current, or you can measure the power directly. You're probably going to measure the current and calculate the power with that equation I had a couple of slides back. And you say, okay, well, it's drawing 56 kilowatts or 75 horsepower, which is about 75% on average. Okay, that 75% of the maximum horsepower for the air compressor. If you multiply this 56 times 3120 times 12 cents a kilowatt hour, you might get $21,000 a year. If you're a large manufacturer, you're probably not paying 12 cents a kilowatt hour. You're probably paying, I don't know, 6-7 cents a kilowatt hour. You're probably also paying demand charges, and we're going to gloss over that for today. But anyway, going back to the performance or characteristic curves, you might be thinking, hey, 75% loaded. Yeah, we're doing great. But if it's inlet modulation, consuming 75% of rated power only delivers about 33% of the capacity based on how modulating controls work. Now, there are not a lot of compressors these days that just use pure modulation all the way down to zero flow capacity. A lot of them use modulation with unloading. So they'll modulate down to a certain percentage, and then they'll start going to load, unload, kind of a mix between the two. In those ones, you can actually choose modulation with unloading, load, unload, or pure modulation. But I have been in a plant before where they've been very lightly loaded, and they're using a modulating control strategy where they had the option literally on the control panel to use load, unload. So that's kind of what this is. This example is designed to represent. So let me get back to what I was saying before. 75% of rated power you've measured, it's only delivering 33% of capacity. So your facility's on average drawing 150 cubic feet per minute, which is 1/3 of the amount that this compressor can deliver, which is fine. It's fine to have an oversized compressor as long as the control strategy is such that you don't waste a lot of energy. This modulating butterfly valve is really very closed, and a lot of the energy going into making that compressed air is fighting against that inlet control valve. So this is an example of what I would say to this facility. I would say two things. Decrease your discharge pressure to 100 psi. Using the rule of thumb, the energy savings would be close to over $1,600 a year. And that's with that 10/2 to the power of 1.6. Well, anyway, hopefully you can get through that calculation yourself. If you can't, just email me. But you stand to save with a 10 psi pressure decrease over $1,600 a year. And the second thing that we have done before, and this is again an example just to replicate it, you can change your control. If you can change your control strategy to load, unload, you stand to save a lot of energy. Why is that? Whoops, here we go. Sorry, go back. Okay, why is that? Well, you can go from this red circle here all the way down to the red line. And so you actually save a fair bit on your compressed air costs simply due to the fact that you're load, unload instead of modulating and fighting against that that inlet modulation butterfly valve. So yeah, you can do that if you want. Another option would be to maybe think about getting a variable frequency drive. The savings in that would be even more than that, than $8,000 a year if you change to a variable frequency drive. In fact, if you had a 100 PSI air compressor that was doing this, I would recommend you just you throw it out and buy a new one that's going to cost you about $30,000 or $40,000 with a variable frequency drive, and you get your money back in 2 or 3 years. Okay. Obviously, you'd want to have someone else like us come in and look at your facilities and make sure that that is the right choice. But I digress. These are the things that you might be able to do today going into your plant. Decrease discharge pressure, change control strategy. Another thing is decrease the leaks. Now I can't without seeing the facility, I can't really tell you how many leaks your facility has. There are a lot of facilities that have basically no leaks because they don't use a lot of valves or pneumatics tools, for example. But a lot of facilities do have a lot of leaks, and you can almost you can tell whether you have a lot of leaks in your facility, and you can probably decrease the amount of costs by doing an effective leak prevention program by 20% easily, just by going back every couple of months with an ultrasonic leak detector, which costs like starting at about $500. They do get pretty expensive for the nice ones. Anyway, so this is an example. You could save $10,000 a year with these effective tips. Other tips I have for anyone about compressed air. It's a very involved subject. And again, this is a whole section of my class, but another tip I have is don't use compressed air unless it's absolutely necessary. I was telling you that it's about 20% efficient getting the electricity from in that compressor cabinet to being compressed air in the end is only about 20% efficient. The rest is going to waste heat. So if you can use a blower instead of compressed air, do it. If you can use a blower in your, let's just say you have a bag house for dust collectors. If you can use a blower somehow instead of pulsing with compressed air, please do it. The savings are immense. Any place that you can do that. Air knives, for example. You can get away with using a blower instead, please do. Control with VFD, yes. Another thing is we didn't get into this, again, it's a long subject, but use larger headers where you can. The smaller the pipes that you have, the more pressure drop is going to go around. You're going to need more pressure drop to get through those pipes. So if you can get larger headers, 2 inches at least, I would recommend. 4 inches if you got a large facility with a lot of compressed air. You're not going to have a huge pressure drop to the other end of your plant, and that ends up being huge. A lot of energy is wasted just pushing air through those at high velocity. And here's another neat tip. You can use coolant air as a heat source. And so, as I was telling you earlier, the double screw compressor, there's a lot of heat in that radiator, and you put your hand on top of that radiator, and it'll be 130 to 150 degrees Fahrenheit. A lot of times that's just vented inside, which is fine, but you can vent it outside in the summer so you don't have to use air conditioners to cool it in the summer, or you can leave it inside in the winter to help heat your facility in the winter. So whether or not your air compressor is venting inside or outside, there's an option for you to maybe use it for heating or maybe vent it outside to reduce costs on cooling, if that makes sense. It's free heat, right? If you have a 100 horsepower compressor cruising along at 100 horsepower, 80 horsepower is going to electric heating, essentially. And so you can use that. You should, if you can. And we've had clients that have constructed some rudimentary ductwork to facilitate this, and it ends up saving them a lot of energy. Okay, so I've talked literally 20 minutes longer than I thought I was going to talk. As you can tell, I'm very excited about the subject of compressed air. Please visit these websites if you can. This is our Industrial Assessment Center website. This is this is the Maine IAC website. Here's our in Alabama IAC website. This is my Rural Energy Program website, and this is another really useful website if you want to go and just fiddle around with your energy usage. There are some online tools and calculators that I've alluded to today on that website. I'm done talking right now. I'm going to have some coffee, and then we'll do questions and answers for as long as you want. I've got all day, so thank you. I'm going to turn this over back to you, Michael.
That was great, David. Thank you for all that information. And we do have some questions. We've got time at least for one of them. Has anybody ever taken that waste heat and used it in another process, like for drying something?
we've recommended it. I don't know if I don't think they actually took the bait. This was an auto manufacturer that was using a lot of compressed air, and they were also using a lot of, they had an oven that needed a lot of recirculating air. So they were blowing in air and heating it up with natural gas and drying paint in an oven. And we recommended they did that. And last time we checked back in 8 months, they said they were still thinking about it. So we have had people that have used it for space heating, but not for process heat, because it's tough. 130 to 150 degrees Fahrenheit is waste heat, right? It's tough to use that unless you can use that as, for example, I don't know, combustion air, inlet combustion air. That would work, but it's got to be right. You got to have that compressor really close by to what's going on before it becomes cost effective. That make sense? I guess this question was from Jody. Yeah? Okay.
All right. Well, that was great, David, and I really appreciate your time and for you sharing all that information. And for those of you that have attended the webinar series, we really do appreciate it. And here's a sort of a link to our P2 program. And so, if you guys have any questions on pollution prevention, whether it be energy efficiency, water use, or chemical use, please contact us at UA SafeState and the Alabama Industrial Assessment Center, and we will help you out free of charge. And especially right now for our program, any in the automotive manufacturer sector, we're available to assist you doing technical assessments, and then also just assisting you with any kind of training that you would be interested in. And so with that, there is the contact information for Ashley Chambers. So feel free to email us, and you have David's contact information and the IAC website. So again, we appreciate your attention, and thanks, David, for an awesome webinar treat, and look forward to working with you some more in the future.
Always happy to help. Thank you. Things are frozen right now. Maybe that's me. All right, I'm leaving.